Hi guys, and welcome back to another video. We're finishing up section 3.2, and what I want to do is I want to cover elimination in a little bit more depth, just like we did last video, substitution, and I want to cover what it means for a system to be consistent or inconsistent, when there is a unique solution to a system, or whether there are no solutions or there are infinitely many solutions. So let's begin by talking about elimination with another example. So the example that I would like to use is this one. So we have that 2x plus 3y is 17 for the first equation, and for the second equation we have 5x plus 7y is 29. So again, this is equation 1 and equation 2. Now note that these numbers, the way how they are, 3 doesn't go into 7, 2 doesn't go into 5. So we're actually going to have to carry out two multiplications here. We're going to have to determine what the least common multiple of what 3 and 7 are, or determine what the least common multiple of 2 and 5 are. So this is what I mean. But what we'll do is we'll determine the least common multiple of 2 and 5, let's say. Least common multiple of 2 and 5. Well, 2 and 5 are both prime numbers, so the least common multiple is just 10. 2 goes into 10, 5 goes into 10, and it's the lowest number for which that's the case. So our LCM's 10. So what we need to do is we need to multiply 2 by, say, negative 5, and multiply 5 by 2. So we're going to take equation 1, the whole thing, multiply it by negative 5, and equation 2, and multiply the whole thing by 2. So now what we're going to do is do this and add these together. So I'll do it in a couple of steps just to make sure that you follow me the whole way through. So we distribute the negative 5 through. We get negative 10x minus 15y equals, and then we take 17 times negative 5, that's negative 85. And on the bottom, we take 2 times 5x, that's 10x. 2 times 7y is positive 14y. And 2 times 29 gives you 58. And now, after multiplying both rows by a constant and then adding them together after that, we eliminate x, which is what we wanted. And then down here, we're going to get minus y is, and then this turns out to be what? Negative 27? Yeah, I believe that's right. So this turns out to be negative 27, and so this means y is positive 27 since we have a negative here. So we divide by negative 1 and we get y is positive 27. Now we can take this solution and substitute it back in to find out what x is. So say we take equation 2 because it contains equation 1 because it contains smaller numbers. So we take 2x plus 3y equals 17. We're going to take equation 1 and we're going to substitute in y equals 27 where y is. This gives us 2x plus 3 times 27 equals 17. 3 times 27 gives you 81. Subtracting 81 from both sides leaves you with 2x equals negative 64. And then after dividing both sides of the equation by 2, we get that x is negative 32. So the solution to this system turned out to be, with larger numbers than before, we get the solution negative 32 comma 27. So this is the solution to this system, and we found it via elimination. So now the next thing I want to talk about is how to identify when a solution is unique, when there is no solution, and also when there are infinitely many solutions to a system. So there's really like three cases that you can have with lines. And I'm going to describe them algebraically and geometrically. So I'll show you what it looks like with the symbols and with the picture. So how about let's start with the picture. I think the picture is the easiest to remember most of the time. So there's really three cases. You have oh sorry, I was off the screen. So we have three cases. We have where there's a unique solution. You know, this means that there's one solution. And there's sometimes no solution to a system. Or lastly, there are infinitely many. This means there is an infinite number of solutions to the system of equations. And it sounds kind of crazy, but any of these three cases are possible when you're solving a system of equation with two variables. System of equation with two variables. And it also has to be a linear system, but not to harp too much on that. Let's go into what these cases look like. A unique solution would correspond to a linear system where two lines intersect in one spot. Let's say they intersect right here. This little circled point, this is the unique solution of let's call this one L1 and L2. So this is the unique solution situation where they intersect in one spot. When there's no solution, it means that the lines are parallel. It means they never touch. There is no solution because they do not intersect at all. So there's no solution in that case. And then lastly, for the infinitely many solution case, the picture is really just a single line. Let's say it's this. Well, we have two equations in our system, but one of them turns out to be a multiple of the other. So we end up getting a single line. Even though it looks like two different lines, they actually turn out to be the same line. And in that case, we have infinitely many solutions. So these are the three cases. Now, and here they are with their pictures. Now let's talk about how they come up algebraically. Well, whenever you solve a system correctly, and at the end of it, you get a single solution, right? You get just for example, say you solve a system, you have some system, and then you get x equals 2 and y equals 3. If this happens, if you end up working out your elimination steps and you end up with something like this, this means that this is a unique solution. Let's say that you're working through your process. Say you've got, so this is like case 1. Now case 2, say there's no solution. Let's say you've got the line, let's say we've got x plus y equals 3, and let's say x plus y equals 2. All right, so notice these are these equations without the right-hand side. If we just focus in on the left-hand side, these two expressions on the left-hand side are the same. They're multiples of each other, right? Well, they're multiples of each other, but then the right-hand side is not a multiple or rather, 3 is not a multiple of 2. So in this situation, there's actually no solution. There's no solution because we can't have x plus y be 3 and that same thing be 2, right? X plus y is just a single number. It can't be equal to two different numbers. So there would be no solution. And lastly, the case where there's infinitely many solutions, algebraically looks something like, let's say you have x plus y equals 3, and then let's say you have 2x plus 2y equals 6. These are actually the same line. They look different, because we've introduced this factor of 2, but it turns out these actually give you the same exact line as each other. So notice that if we solve for y, we get y equals, if we subtract x from both sides, we get negative x plus 3. And then here, if we solve for y, we can just get 2y is 6 minus 2x, and then divide by 2, and then we get y is 3 minus x, or in other words, ooh, oh wow, I was off the screen there, I'm so sorry. Y would be 3 minus x, or minus x plus 3. So notice, the point being here, we got the same, we got it here and here, we got them to be the same. So this is actually just the same line. So it corresponds to the situation where you just have this single line and anything is a solution that's already on this line. So there are infinitely many solutions. So let's quickly summarize. For a linear system with 2 variables, you either have a unique solution, no solution, or infinitely many solutions. Their geometric descriptions look like this. You either have one single intersection, no intersections, or infinitely many intersections because they're actually right on top of each other. They're the same line. And then algebraically, you have a unique solution if you solve the system and just get one nice answer. There's no solution when you end up getting something that's a contradiction. So this is a contradiction. And lastly, if you end up solving a system and they're multiples of each other, or in other words, if you end up solving a system and at the end you get some kind of a trivially true statement like 0 equals 0, or say 7 equals 7, if you solve the system and then you end up at a spot like this, that means that there's infinitely many solutions. All right, I think that's the end of this video. This one's a little bit longer than I had wanted it, but I think this is okay. So in the next video, we'll approach section 3.3, which will involve some more applications of the substitution and elimination method. There'll be some more applications of systems of equations with 2 variables. So that's it for this one, guys. We'll see you in the next video in section 3.3.